Okay, in this project, we measured the thrust density of model rocket motors using a fixed load cell setup. Our goal is to quantify thrust density and calculate uncertainty, error, and error propagation using standard measurement techniques. This project is relevant to hobbyists, educators, and small-scale aerospace designers who need consistent engine performance data. The thrust data we collected can inform safer and more efficient rocket design. Using LabVIEW to log thrust data and applying statistical analysis, we calculated average thrust and its corresponding uncertainty. Our calculated thrust densities stayed within acceptable error bands using a logarithmic function, making our results suitable for most hobbyist applications. We found a maximum thrust density of 800 and a minimum of 400. This calculated thrust density is unitless, where a higher thrust density number corresponds to a higher thrust to volume ratio, with an average uncertainty of 3% for a 95% confidence interval.
The cost associated with constructing, testing solid rocket motors is extreme, especially for single-use motors. There are many different propellant mixes and motor sizes used in both commercial and hobby rocketry. The purpose of this experiment is to find the equation that relates the average thrust density and the mass of the propellant used. This data can specifically apply to hobby rocket motor manufacturers, who can then use this information to predict the properties of motors as they scale their sizes using the same propellant. We will test several motors that represent a range commonly used in hobby rocketry. We chose types A through D with the goal of generating repeatable thrust characteristics for each motor class tested within 3% of what we expected based on manufacturer data. From this, we can then extrapolate an equation that can be applied within that range to further develop these motors. We explored several options for motor mounting and data acquisition. We ultimately selected a fixed vertical jig made from 3D printed parts, as it was quick and dirty but sturdy, and used a load cell connected to LabVIEW to capture the thrust data in real time. The load cell was selected was rated for 10 kilograms, and we connected it to LabVIEW via a MIDAC and an amplifier. Each motor was mounted vertically, fired downwards into the load cell. Thrust was recorded through the LabVIEW at a high sampling rate, and we measured the weight of the rockets before and after the launch to get the propellant mass. Cut it there, because these are in the wrong order.
When it's supposed to be videoed in
Well, because I didn't go to measurement devices after this, and I didn't tell all my variables. The important variables that we were measuring were the mass of the propellant and the thrust. For the mass, we used a scale in the MA LabWorks, and for the thrust, we used our load cell setup pictured in Figure 3. One of the weaknesses of this setup was the ignition method, and we had issues getting some of the igniter plugs to fire, and as a result, some of the data was skewed, and so we removed those tests because we knew that the thrust data was bad. And in review, the measurement devices that we used were a 10 kilogram load cell, an amplifier, a MIDAC, LabVIEW, and a digital scale. So here's an example of how we measured a motor as it tested. So you can see as it fires, there's the initial spike in voltage, and then it continues throughout the sustainer. And so we're able to take that voltage and then use a linear fit to compute the thrust. Some alternatives to this would be using a rocket sled, which you would measure the position and velocity, and then from there you can find forces and accelerations. Another option would be spring displacement, as you measure the displacement of the spring over time. These options ultimately would require a lot more time and effort to refine them, and so that's why we used a load cell.
Our primary goal was to predict average thrust characteristics of a rocket motor based on the mass of propellant used. This slide shows our raw data, and as we mentioned, we threw out the highlighted portion of our data because of a user error in the recording. Thrust data was recorded using a load cell and logged through LabVIEW. For each motor, we recorded thrust over the burn time and extrapolated the average thrust over the burn. We used standard statistical tools, including sample mean, sample standard deviation, and a confidence interval of 95%. And because we had a limited number of trials, we applied students' t distribution to estimate uncertainty.
Because we were only able to test 3 rockets for each class of motor, the central limit theorem cannot be applied, so we use students T instead. Figure 4 is a demonstration of what students T distribution looks like for our data. The confidence interval is 0.72 for a Class A motor, 0.68 for a Class B motor, 0.79 for a Class C motor, and 1.52 for a Class D motor. We use a two-tailed hypothesis t-test to compare our measured average thrust with the manufacturer's average thrust. Table 3 contains the data used to accept or reject the null hypothesis, which is that the average for our measurement equals the average of the manufacturer's measurement. Based on our t experimental values and the t actual values found in our confidence interval, we do not reject the null hypothesis.
For the chi-squared analysis, the motors were grouped by propellant mass. The average thrust by motor size was listed and compared to the expected thrust from the manufacturer's specifications. The chi-squared was found with the table using degrees of freedom of 11 and a significance of 0.05 as our confidence was 95%. This resulted in 19.675. The expected value was calculated to be 0.89636. As the expected chi-squared value falls within the interval range, we fail to reject the null hypothesis, and we conclude that our constant confidence interval is fair, as shown in Figure 6. To calculate uncertainty, we first need to identify the governing equation, where thrust density is the average thrust over the mass of propellant. We calculate the partial derivatives of thrust density with respect to force and mass. These partials are used in the uncertainty propagation equation. The average thrust and mass for each rocket size was used to calculate the uncertainty for each rocket size. The uncertainty in the load cell used to measure thrust and the uncertainty of the scale used to measure the mass of the propellant are also used as UF and UM. To report the uncertainty of thrust density as a percent, we need to calculate the thrust density, which we get from plugging in the average thrust and average mass of propellant into our governing equation. We then divide uncertainty by the density to get percent uncertainty.
In summary, during the design phase, we selected a 3D printed mounting jig for simplicity and repeatability, a 10 kilogram strain gauge with an amplifier, and LabVIEW for data acquisition due to its integration with our existing DAQ hardware. In the method section, we explained how we measured rocket thrust and why we chose each component. We then went into the results where we calculated the confidence interval, students' t distribution for each motor, and performed the chi-squared analysis. We then did the uncertainty analysis where we calculated the uncertainty propagation of our governing equation for thrust density. We propagated uncertainty through to thrust density calculations using both theoretical and observed values. No Fourier or signal filtering tools were required as the thrust time signals were smooth and low frequency. Our final data set includes thrust density values for each motor class, which can be seen here in Figure 7. They are accompanied by uncertainty bars to reflect measurement confidence. These values provide a useful metric for comparing motor performance beyond total impulse alone. Our final thrust density uncertainty was within our 3%, meaning that our methods of measurement were successful. To improve this analysis in the future, the problem statement could be narrowed to include only how the theoretical thrust density of a single rocket class, such as a Class A, compares to the calculated thrust density. This would allow for more data to be taken and for that data to be more easily comparable. This would allow for fewer variables, resulting in higher accuracy and lower uncertainty. And then for our references page, we have these three references, and as our Fourier's analysis was not used, we have included that in the appendix.